This tutorial shows the calculation of the chi-square goodness of fit test and the interpretation of its results in R, followed by reporting those results. The chi-square goodness of fit test is used when you have a categorical dependent variable and want to test for a difference between observed and expected frequencies. For example, I have a categorical variable depicting the place of living, urban, suburban and rural. The goal now is to test whether there is a substantial, aka significant difference between the observed distribution and a theoretical distribution, for instance, equal distribution. As a first step, after importing data, I need to put the observed frequencies into a vector. This is done by using the table function and the dependent variable within it. Running the table function shows me that I have 11 persons from rural county, 25 from suburbs, and 15 people living in cities. Next, I need to specify a vector with the expected frequencies. If it is an equal distribution, I assume I need to put 1/3 3 times if I have 3 categories. The sum of the probabilities within always has to be 1. Now I can get to the chi-sqaure.test function and put the 2 arguments in it. First, x equals the observed frequencies. Second, p equals the expected frequencies. You will then be presented with the results. Your focus should be on the p-value. If the p-value is below the predefined threshold, for example 0.05, you can reject the null hypothesis. Reminder, the null hypothesis assumes no difference between observed and expected frequencies. In my case, I defined alpha as 0.05 and can therefore reject the null hypothesis, because my p-value is 0.047 when rounded to 3 decimals. For the second expected distribution, the chi-square goodness of fit test shows a p-value of 0.46 and we therefore have to retain the null hypothesis. Finally, I can conclude that my observed frequencies are different from the expected frequencies, in my case, equal frequencies. After you've observed the significant difference, you should follow this up with the calculation of the effect size, Cohen's omega. The first step for this is installing a new package called rcompanion, using the install.packages function and the library function. Please note that you have to put rcompanion within quotation marks within the install.packages function. The second step is using the cohenW function, which calculates Cohen's omega, also referred to as Cohen's W because of its similar look. The observed and expected frequencies have to be entered into this function. The syntax is the same as for the chi-square test function. After running this line, you will only get one number as output, Cohen's omega. The third step is to classify the magnitude of the effect. If similar studies in your research field exist, compare your effect size with the given one. If no comparable study exists, use the common thresholds within your research field. If those are also non-existent, you can refer to cohenNW, a power primer on page 157. It shows 3 thresholds for the chi-square goodness of fit test. If your omega exceeds 0.1, it is a small effect. If it exceeds 0.3, it is a medium effect, and if it exceeds 0.5, it can be classified as a large effect. In my case, my Cohen's omega is 0.346 rounded to 3 decimals, which can be classified as a medium effect because it is above 0.3. When you're done, you have to write up the results. First, one formulates whether the observed and the expected frequencies or distributions are similar or different. For this purpose, the chi-square value is reported together with the degrees of freedom. Within the chi-square goodness of fit test, the degrees of freedom are always the number of values of the test characteristic minus 1. This is followed by the p-value, and in the case of a significant difference, i.e. effect, also the calculated effect size, Cohen's omega, or sometimes also referred to as Cohen's W. Finally, the magnitude of the effect size is classified, for example with Cohen 1992 or the respective research field specific thresholds.